Record. All right. Good afternoon, everyone. I hope you all are doing well. From this lecture onwards, for a few lectures, I have actually written down things for you because trying to prepare the PowerPoint is really too much because it has a lot of figures and mathematical notations. So what I've done basically, I've written this down and I will be explaining using these notes that I have written. Okay. So last time what we talked, do we have any questions so far?
I think there was a question about assignment.
Okay, where's the question? Can you ask me, or where is this question? What was the question?
I think in the assignment it asks for 3D plot and like can we use tools like MATLAB to plot it?
In the assignment, it's asked for 3D plot. Can we use tools like MATLAB to plot it? Okay, if it's a 3D, sure, of course.
Okay, thank you.
You're welcome. Anything else? Okay, so basically, just a reminder to all of you, you guys will be having your quiz on Tuesday. So please make sure that you are available online at sharp 12 noon because your quiz will be uploaded. You can see your quiz in Moodle at exactly 12 noon. As I mentioned earlier, and I'm reinforcing what I just said earlier, please do not copy, do not use your group chats, and do not share your answers because trust me, I always have people who will inform you what's going on in your chat. It has always happened in the past, it will always happen in the future, okay? So be honest to yourselves, and honesty is the best policy. Even if you don't know how to solve it, please at least try your best, and I would value that more than you cheating. Solve the question. I'll be providing a Zoom link to you guys. I'll be available on Zoom in case you have any questions regarding the quiz. You can just join the session, ask me your question, and you will be having like time till I don't know 1:15 to submit the entire handwritten solution. That means like keep the last 10 to 15 minutes for scanning and uploading. Other than that, you have time to write. You have to upload your scanned solutions to Moodle. There will be a link provided. Okay. So your quiz is on Tuesday. I'm informing you. If your friends are not there today, please inform them in advance. No excuses will be accepted because this is the second time I'm informing. Okay. Now let's get back to what we have seen. So we were talking about unimodal function. Sultan, can you explain to me what is unimodality?
Unimodal function is
unimodality. What was unimodality?
Unimodality is a certain range where we have only one minimum.
Okay, and
it is either increasing or decreasing.
Yes. So basically, what I did over here is I tried to let me make it. Okay, I tried to redraw it so that you guys could have a different perspective of how it works. So basically, a unimodality function, as Sultan said, has only one minimum or one maximum. So minimum is valley, maximum is peak. So it's either one value x star whose functional value is the greatest or the smallest in a given range, okay, or in a given interval. So the definition of unimodal function f of x is given here within some given interval a and b. So a function f of x is said to be unimodal within this function if there exists some point x star in this interval such that for any 2 points x1 and x2 that I take in this interval where x1 is less than x2, these two conditions always hold. Okay, so do you agree with these two conditions? Is it clear? So for example, if for example, x star is greater than or equal to x2 in this case, then f of x1 would be greater than f of x2. That means this would be such a function, right? And in other words, if it's the opposite, then we would have such a function, okay? And the third case would be if it is somewhere like this. So the midpoint would be this point over here, the x star. So x star would be here, x star would be somewhere here. So these are the three cases which actually are covered by this condition or by the definition of the unimodal function, okay? Now you may ask, okay, what if the function is a multimodal function? That means you have a function where you do not have just one peak or thing, one peak or one valley. You have multiple of them. So in that case, what you can do is actually you can divide this into smaller functions, and each of them could be one unimodal interval, and you do the unimodal search within each of these intervals, sub-intervals, okay? So that is how you can treat a multimodal
Professor.
function as a unimodal function. Yes, sir.
Could you please zoom the PDF?
Okay, zoom. Is it zoomed enough?
Yep, thank you.
Okay. Did you understand, or should I repeat? So basically, if your x star is over here, we know that we can actually remove everything after this. So we discard between x2 and x1. If x star is, sorry, over here, we can remove this part. If x star is between x1 and x2, remove these two parts. So we are reducing the what we call the interval of uncertainty, okay? So the unimodal function can also be a non-differentiable or even a discontinuous function. For example, you see that this is not differentiable at this point, right? At these points, this function is non-differentiable or it is not continuous. Okay, so I'm sorry, it's non-differentiable at this point and it's non-continuous at these 2 points, right? So even in this case, we still can have define a unimodal function. So in this function, this point would be the minimum. And in this function, this point would be the minimum value, okay, the value. Now, today what we'll be looking at is we'll be looking at techniques which we call elimination methods, which will help us reduce the interval of uncertainty, okay? So basically, so last time we studied about some techniques where we talked about bracketing method and open methods, which helped us find minimum value, okay, local minimum, okay? Now we are assuming that if I give you a unimodal function, okay, as our friend had asked last time, how do we determine a good or smart starting point, okay? So in today, this elimination method will help us actually find that interval or that smart interval or that smart starting point, okay? So basically what you do is, given a unimodal function, you will start with some guess, some point, and then using any of these elimination methods, you will find that interval of uncertainty, which ensures that your minimum point or your minimum optimal point is within that interval, okay? So basically today what we are going to do is we are going to learn techniques how to find the interval of uncertainty. Is it clear? Okay, so let's begin. So if there are any questions, just interrupt, okay? The first technique to find this, the interval, is known as unrestricted search. So basically now we are only focusing, as so far we are talking about only univariate functions. So we assume that f of x is just one variable. So we just need a two-dimensional plot. And on that two-dimensional plot, basically what we are doing is we are trying to search for the interval of uncertainty, some interval which will guarantee that our single minimum or maximum point lies within that interval, okay? Is it clear what our problem statement is, everyone?
Yes.
Good. So unrestricted search. So the first technique is unrestricted. And why is it unrestricted? I will tell you shortly. So one version of the unrestricted search is when you search with a fixed step size. So basically, this is something very, obvious, and probably this would be what you guys would think of if I would have asked you to, okay, find an interval. So now basically, what you want to do is you want to find that interval AB And within that interval, then you can apply the bisection method, the secant method, or what other method you want in order to find the minimum point, okay? So this elementary approach, what it uses is it uses a step size. So in every step or any iteration, it changes or it finds the next point to be evaluated using some constant step size. Okay, so let's denote our step size by this delta. Okay. So what we do is let's start with some initial values. So now what I've given you, so basically what you have is some function, some unimodal function. Keep that in mind. Okay. And I'm saying start from some point. Okay, I have a figure over here. Suppose this is your function f of x, and I'm asking you to start some point. So assume that you start at this point. Okay, so your first initial guess is x1. Okay, over here I've just written 1, not x. Okay, so just start with some random point, initial starting point. We call it x1, and then we do the following. We find the next point x2, which is this point. And how is x2 found? x2 is equal to x1 plus that step size, which is delta. Step size is something that you define. Okay, you can define it to be 0.1, 0.5, 1, whatever you want. Okay. So over here, so what we do is we do x2 is equal to x1 plus delta. So the distance between these 2 points is delta. Okay. Now we evaluate the function. We evaluate the function at these points, x1 and x2. So this is f of x1. And this is f of x2. Now, if f of x2 is less than or equal to f of x1, it means that this function is still decreasing. Okay, that means there is a chance. That means obviously the minimum point will not be within this interval between these 2 points. So now what we do is we keep going. That means now from x2 we do x2 plus delta, which will give me x3, this point. Okay. And now I take the functional values at these 2 points. So this becomes my new x1. So this part is discarded. So we do not have to worry about this part. So this 2 becomes my new x1, and this 3 becomes my new x2, right? And I keep doing this. Now, again, I evaluate the function and I see whether f of x2 is less than f of x1 or not. It is less than f of x1. So again, it means that I have to start from here plus delta, and I go to my new point. So again, this point is this part is discarded. So now this becomes my new 1, and this becomes my new 2, right? Now I have 2 points. Now I evaluate them. Now, if these 2 points are so now then I check the what is that elimination condition. Whereas sorry, I check the unimodality condition. This condition, I check this. So if at some point this happens, so now we know that our x1 value is between x1 and x2. So at this point, f of x1 is equal to f of x2. Okay, here, and assume that they are equal. Okay, this is a bad drawing. So if they are equal, we know that the minimum point is in here. So then we stop, and then we define this point as my x1 or my xl, which is my lower point, and this is my x upper point. Okay, and therefore this is the interval in which I have to apply one of those algorithms, optimization, algorithmic methods that we studied in order to find the minimum, local minimum point. Okay, so this is known as bracket. Okay, is it clear?
What if the delta is big enough so that we from the 0.1 go strictly to 0.3?
Yes,
then we can miss
you can always choose delta to be that, but keep in mind that if, as you mentioned, so assume that delta is big enough that if I'm at x1, I add delta and I get to this point, right?
Yes.
Is that what you're saying?
Yeah, then we would miss them.
Yes, so you would have this guy in the middle, right?
Yes.
But the thing is, this your search space would be very large. You have to search this area. But over here, I'm giving you a very small area. I'm guaranteeing that your midpoint or your optimal point is within this small area. So the thing is, it is a good idea. See, there's a trade-off. If you take a big delta, you will get the interval faster, but you will not get a fine coarse interval. You will have to do a search. And when you do binary search, it will take more iterations. I'm sorry, bisection. If you apply bisection method, you will have to divide it. You will have to do more number of iterations to divide this interval. But the other thing is, if you take a small delta, okay, It will take a longer time to find the interval, but if you find the interval, once you find the interval, it will be much smaller, and therefore any of your graphical methods would get you to the minimum point much faster. Okay, so do you understand the trade-off?
Yes, yes.
So a bigger interval means more iterations for the graphical methods to find the minimum point. A smaller interval means lesser iteration. But again, getting a bigger interval is easy because you don't have to have so many steps in dividing. Okay, you'll just do it in one step. But a smaller interval, probably you will have to go 3 or 4 times. But on the other side, you will get a smaller size search space where you can apply your univariate optimization method. Okay, is it clear?
Yes, yes.
Okay, any questions? So this was basically the search method, undirected, unrestricted. And why is it called unrestricted? Because you do not have an interval given over here. I do not say that, okay, the initial point that you start with should be within the interval A and B. There is no interval. I'm giving you a unimodal function, and I'm saying choose a point on that function. Okay, choose a point and evaluate it. And from that point onwards, you just start in one direction. So you move in one direction, starting from a given point. Okay. So that's why it is called unrestricted. There is no bound. There is no A-B interval bounding the unimodal function. Now, what we can do is we can further improve this method. The problem with this is that we have a fixed step size. I mean, every time we are adding only delta, delta, delta. That means the size of this interval is always changing by delta. So what happens if we kind of, accelerate it? Instead of just using delta, we use we scale it, okay? We use some kind of gamma delta instead. Now let's see how this helps, okay? So basically, the accelerated version of the unrestricted search basically tells us that, okay, so this is the motivation. Why do we need to accelerate the step size? I want you to read this and I'll ask you what it means. Everyone read this. I'll randomly ask one of you to explain this. Okay, Ablay, can you please explain us? Ablay,
Hello, Professor. Yes, yes, yes.
could you please tell us what this means? Why is this, how does this motivate us to use an accelerated step size? What's the problem?
So in case of function where the minimum point is say to be 5,000,
50,000.
50,000, and if we don't know the location of this point, we choose 2 points such as x1 and delta that are 0 and 0.1, and so that we can evaluate the function 5,000,001 times to find this point.
Yes, thank you. So suppose this point that you want to find is at some x star is equal to 50,000, okay? And as I told you, you should start with some initial point. Now, suppose I choose my initial point to be some point x, which is 0, in this case 0. And the delta size of my step is 0.1. So every time I can only go 0.1, 0.1, 0.1, 0.1, 0.1 times till I get to this minimum point, okay? So that means I have to do these number of functional value evaluations to get to that point. Okay, so you see that this has a lot of work to do, right? So this is not good. So if I have a step size, if I know that this is very far away, why don't I take a bigger step instead of taking smaller steps? Okay. So the idea behind this is that as long as you are far away from the local minimum, you take big steps. While you approach the local minimum, you reduce the size of your step. Okay. So that is the intuition behind this approach, and it is known as accelerated step size. So it is basically the same as what we have seen so far, except that instead of having delta to be fixed, we have every time delta to be changing. So it is some function of gamma, and where gamma is some value greater than 1. Okay, so if we look at this figure, we see that, okay, in the same example, if we start with x1, and initially I take gamma to be 1. Okay, so I have a step size of delta. And I see that, okay, even after doing this, I am not able to enclose the minimum point. Okay, I do not have any one of those conditions specified over here, these 3 conditions. Okay, so if these 3 conditions do not hold yet, so what I'm trying to do is I'm trying to find an interval. So when I'm trying to find an interval A, B, in which I want to do my graphical method, so basically only this condition should hold, right? Because I want to enclose my minimum point within 2 points, right? So this condition should hold. As long as this condition does not hold, I keep moving. So now if this is not true, then I try to multiply it with some gamma, say gamma becomes twice. So say this is 2 gamma, 2 delta. Okay, and so my x3 point is not equal to delta but 2. So I take twice the step as earlier to find the next point. And if it doesn't lie, again, if the third condition is not satisfied, I take it to be 3 delta. I take a much bigger step. So now I get my next point. Then I evaluate the functions at these 2 points. And since the minimum point lies within it, then this would be my interval A, B. And then I apply bisection, secant, regular, falsy, whatever method I want to find the minimum point within this interval. Is it clear? So basically, as long as you do not satisfy the third condition, where's the third condition? This condition, you keep increasing the size of your delta. Okay? So this will obviously be an improvement to our fixed step size approach. It will take less a number of iterations to find this given interval. So if that is clear, now let's move to the next search approach, which is known as exhaustive search or simultaneous search. No questions? Okay. So so what happens over here now, unlike the previous method where we did not have some interval, over here I'm giving you an interval, okay? So this guy, so the previous was unrestricted search because there was no specified interval for the unimodal function. You could have started from any point as the initial point, but over here I'm giving you an interval. So I'm asking you to find the interval of uncertainty or the A-B interval or a smart starting interval within some given interval, xs and xf, starting interval and starting point and finish point, okay? So basically, remember, exhaustive search, it requires an interval, okay? So we determine the interval or define the interval by 2 points, x of s and x of s, which is the starting and finishing points of the interval of uncertainty, okay? So what we do basically, the idea behind this is that we define some n value, okay? We say that, okay, I want to divide this interval into, I don't know, 5 equally separated intervals, equal size intervals, okay? So each of these intervals, the size or the distance between the 2 consecutive points is the same. So if I want, so what I say is, so this method consists of evaluating the function at a predetermined number of equally spaced points, okay? So in advance, I tell you, okay, use, for example, exhaustive or simultaneous search to find an interval for some given function, unimodal function f of x within xs and xf, and n is equal to, say, 7. So basically what you have to do is you have to divide this given interval from xs to xf into 7. So you should have 7 points, and therefore you will have 8 intervals or smaller intervals within this large interval. Okay, so n is equal to 7 means you have to write x1, x2, x3 till x7. So divide this, okay, and the length of this interval would be obviously xf minus xs, right? This point minus this point would give you the length, which is denoted by L naught, L 0. Okay, and so I ask you to divide it into smaller points, and smaller intervals, and each interval is of the same size, and you have to evaluate the function at all these points. So if n is equal to 7, that means you will have x1 to x7. You find the functional value for all those points from f of x1, f of x2, f of x3 until f of x7, okay? And what you do is you have to do the test, the elimination method test, to see in which interval the condition occurs. That means the minimum point lies between two functional points, okay? So let's assume that this x star, okay, up here is this point. So say that this xj is basically our x star, okay? Then the final interval that you would have would be the interval from x3 to xj plus 1. That means xj minus 1 to xj plus. That would be the length of your interval. So, and we know that the size of each interval is also equal. Therefore, we would have two intervals out of all the n plus 1 intervals, okay, times the length of the total interval. That would be the length of the final desired interval. Is it clear? Is it clear how I got this? Yes or no, guys?
Could you explain it once more?
Okay, let's explain it one more time. So basically what you have to do is, if I give you some interval xs and xf, you find the length of the interval. So L naught would be the distance from the distance between xs and xf. Is it clear what L naught is? Yes? Okay.
Yes.
Now, so if I tell you that, okay, let n be equal to 7, then what you do is you have to choose 7 points within this interval such that the distance between each of them, that means it divides this interval into smaller intervals, and the size or the distance of each of these smaller intervals is equal. Okay, so this should be equal to this should be the distance should be equal to this. So if I have 7 points, I will have 8 intervals, right? If you have a line between 2 points and you have 1 point which divides it, so you will have 2 intervals. So 1 point gives you 2 intervals, 2 points give you 3 intervals, right? So that's it. So always, if you have n points, you will have n plus 1 number of intervals. And I know the size of all these intervals are the same. Now what I want to do is, so then after you find these points, you find their functional values. Okay, so find f of x1, f of x2, f of x3 until f of xn. Which is 7. Okay, so when you do that, you have to check this test. You have to do this test. This test is important. This guy, because we want this condition. Okay, we want to find the best interval within which the minimum value lies. Okay, so you find the functional values and you do this test. So the case which gives, so whenever that is satisfied, that test is satisfied, what you can say is, so as I said, so assume that xj is my minimum point, x star. So how do I choose my reduced interval? I say that the interval, the point before it, okay, so if this is xj, means xj minus 1, and I take the point after it, xj plus 1. So I have 2 intervals, right? So the length of my final interval within which I have to do the bisection, or I don't know, Newton method, would be xj plus 1 minus xj minus 1. So I'm taking 2 intervals, 2 out of n plus 1 intervals, right? And multiplied by L naught will give you the size of the final interval. L naught is the size of our total interval. We divided n naught into how many intervals? N plus 1 number of intervals. And how many of them do you want to take in your final interval? You want to take 2 of them. One before that point x star and one after that, so that you can do the search within it. So you will have 2 divided by n plus 1 L naught as the size of the final interval. If I tell you that you have to have n number of points or evaluation points within this given start and final interval. Okay, is it clear?
Yes.
So do you know, so this is very important. Okay, well, this is very simple, because later on we'll find more complicated, we'll see more complicated equations for Ln. So given L naught, given n, you should be able to find the length of your final your final interval. So these are questions that can come in your quiz, so pay attention. Okay, now we go to dichotomous search, which is another type of not exhaustive, it's a total different search. It has nothing to do with exhaustive search, okay? So we saw unrestricted, we saw exhaustive, and now we are looking at dichotomous search. I'll give you 1 minute to read this, and then I'll ask you whether you understood or not. If not, I'll explain. Please read this. Okay, anyone volunteering? No? Okay. So compared to the exhaustive search that we just saw over here, we saw that in exhaustive search, if I give you endpoints, you had to evaluate the function at all these points, right? In order to check whether the x star, f of x star, lies between f of x2 and f of x1, right? This was the condition that we wanted to check. So we had to evaluate the function at all these n number of points, okay? But in dichotomous search, what you do basically is you try to divide this interval between xs and xf into almost half in each step, okay? So it's also known as sequential search. So let's see how it works. So basically what you do is you place the two experiments. Two experiments means those points that you choose, okay? Every point that we choose is called an experiment. So we try to place it as close as possible to the center of the interval. So if the length, so we know that the length of the interval is xf minus xs, right? And L naught, so that is L naught, and L naught half would be this point, exactly the middle point, right? Now, what this guy does is it tries to, so for some delta value, which is positive, okay, so for some delta value, which is positive, we try to find the two experiments, the 2 points, which are almost nearly close to the midpoint. So we take, I don't know, delta half and delta half. So if this is the midpoint, then the midpoint minus delta half would be x1, and the midpoint plus delta half would be x2. So that my two experiments would be placed at these 2 points. Okay, so basically x1, your new point would be half minus delta half, and x2 would be L naught half plus delta, okay? And by doing so, what you do is now you have 2 points, you evaluate the function at these 2 points. The good thing about this compared to the previous method is that over here, when you wanted to evaluate, you could only eliminate each interval, each smaller interval one by one. But over here, what you do is you can eliminate almost nearly half the interval in every step. So if I check this condition, this test, unimodality test over here, and if either one of the condition hold, then actually I can eliminate either this half or this half, which it's not half or nearly half interval, okay, which is a large portion as compared to the previous search method. Okay, so the new interval of uncertainty that you get would be L half plus delta 2. So for example, if, let's say, so let's see, the function is here. So let's say this is the function, okay? So if I know that this condition holds, so this is not true, then what I can do is I can eliminate everything after this. And I take this as my new interval. And then I apply the same thing. I take the half and I take delta plus, delta minus, and I do the same thing. So with this method, the dichotomous search, you eliminate nearly half of the search space in every iteration. Okay. So in general, if you have n number of experiments, well, n is obviously positive because you're choosing 2 points every time, right? So n is a positive value. So if I say n is equal to 3, I'm not sorry, if n is equal to 4, 6, so you can find the final length of your interval, the smart interval, by using this equation. Okay, because every time it divides by nearly n half, L naught half. And so I want you guys to actually derive this equation and show me how this is got, how we get this, okay? So as we saw, L of n for the final interval would be as such, given n. And also over here, if I give you some even n value, you should be able to actually derive this, okay? So do this. This could be in your quiz, okay? I'm again answering. If something is not given in your slides, it doesn't mean that it's not important. It means that you have to work it out. Okay, guys. So I want you to tell me using using the approach or the strategy that I just mentioned, how we can derive L of n for the dichotomous search approach. Okay. Any questions?
Yes, I have a question.
Yes.
How many times do you have to conduct this kind of experiments? Here it says n, but what
And
is n?
it will be given to you either in your exam, or it is something that you can define. It depends on how small or how big you want your search interval to be. If you want your search interval to be big, n could be like 2. It would give you a bigger search interval. If you have n to be like 6 or 8, obviously you will get a much smaller search interval. And therefore, for example, if you want to use the graphical methods where you have to derive a function, that means you have to find the derivative. Obviously, you won't have to do much of that because you'll have to find the derivative only 1 or 2 times to get to the minimum point, right? But if your interval is very big, n is some very small value, okay, probably you will have to do more, find the derivative or find the functional value of those derivatives more often if you use one of those methods, graphical methods, okay?
Fine, thank you.
Did I answer your question? Is it okay? So n is up
yes,
to you.
You answered.
No?
Yes.
So n is up to you. Depends on how refined you want your search interval to become. Okay. So for smaller value of n, for n, for example, if it was 2, I would only divide this into, I would do this division only once because I already found my 2 experiments, x1 and x2. But if n is equal to 4, this will further divide one more time, and therefore I'll get a much smaller search interval. Okay. And within that interval, I can then apply one of my graphical methods and get my solution.
Okay.
Okay, good. Now let's look into interval halving method. Now, in this previous dichotomous method, I said you nearly eliminate half of the interval in every iteration, okay, depending on the value of n, right? Okay. But now the other method is interval halving method. And in this method, what you do is you exactly remove 1/2 of the interval. You do not remove like this. You don't have this plus delta half. Okay. You exactly remove at half. That means at L naught half, that means even this part or this portion is removed depending on when this condition is satisfied. So you divide in every iteration exactly half of the interval and not nearly half, okay? So, but in this example, in this experiment, I'm sorry, in this method, you require 3 points. You require 3 experiment points in the first stage, and then in every stage that follows, you only need 2 experiment points. So to start off with, you need to start with 3 points. Then in every stage or every iteration that follows, you only need 2 points, okay? But initially, 3 points are required. Okay, so we will look at this and let's see how this works. So again, we have given some interval L naught between XS and XF, okay? So what we do is, so for example, if this is XS and this is xf. So it says that divide it into 4 equal parts. 4 equal parts means divide this half, divide this half, divide this half. So I have 4 equal parts. That means I need 3 points, right? 3 experiments, 1 experiment, 2 experiment, 3 experiment. Is it clear? So let's call the middle half. So any interval, when you divide it into 4 halves, means you will actually first divide it into half and then each half into half. So this half would be definitely the middle point. Let's call the middle point x0. And let's call the other points x1 and x2. Is it clear how I have numbered my points? So this is how, I'm sorry, labeled my points, okay? So you divide it into 4 equal parts and label the middle point x0 and the quarter interval points as x1 and x2. Now, what we do is find the functional value at these points. Find f of x1, f of x0, and f of x2. There are 3 cases that may occur, okay? Let's look at these 3 cases one by one. If f of x2 is greater than f of x0, and f of x0 is also greater than f of x1, that means you have some function, say like this. F of x2 greater than f of x0, f of x0 also greater than f of x1. So this is called case 1. So what we can do is we can remove which part? Everything after x0, right? So we know that the midpoint definitely will not be existing in this half. So we can just eliminate it. Am I right?
Yes.
So this is called case 1. So this is case 1. If you look at this, I've drawn the same thing. So if the functional value is decreasing, so if your function is unimodal function is something like this, okay, what you can do is from here onwards, just eliminate it, remove this. We don't need this. So only we have to search within this half. This is case 1. Easy. Now, case 2 similarly is the other way around. If f of x2 is less than x0, f of x0, and f of x0 is less than f of x1, then what you do is you eliminate the interval xs to x0, right? So you then eliminate this part because we know that the function is decreasing and it will probably be here somewhere, the midpoint, sorry, the optimal minimum. So we can eliminate the first half. So we are eliminating exactly half of the interval every time. The third case is if f of x1 is greater than x0 and f of x2 is also greater than x0. That means the function is something like this. Okay. Again, it divides it into, it eliminates half. How does it eliminate half? It removes this guy before x1. It removes this guy after x2. So now we again have half, right? But they are equally divided. So this will also be half. Then what we do in the next step is we test whether the new interval, that means this is my new interval, xf and xs. I'm sorry, xs and xf. Okay, so this will be my new interval. And whether it satisfies either you find the point, or if not, you keep reducing the point. And it's L0, you keep reducing until it becomes equal to some epsilon value, which is a very small value, okay? If this is satisfied, you stop. If not, then you do everything again. So now you have again, what you do is now you have 2, so you have to find now 2 points, right? So again, you divide this part into half, this part into half. Now you get 4 equally divided intervals and you repeat the same test as before again. Is it clear? So in the first test, in the first iteration, we took 3 points. Now in the next iteration, we do not need to take 3 points. We only take 2 points because we already have these points. Because we already have a midpoint in each condition. We have this point, we have this point, we have this point. We only have to take the 2 other points, which would be this point and this point, or this point and this point in this case. Is it clear?
Sorry, Professor.
Yes,
Could
sir.
you please remind, how do we know that the function is unimodal?
A function is unimodal. Well, we go back to this definition. If these conditions hold, this is the definition of function of unimodal. So if there exists some x star, and for any 2 points x1 and x2 within some interval, where x1 is always less than x2, this is a very important condition, okay? Then if the x star lies after x1. I mean, sorry, if the functional value of x1, okay, is greater than the functional value of x star, then this condition would always hold. That means we can remove this guy. Otherwise, the other, it's this one, or it would be this condition where x star, functional value of x star is less than x2 and it's less than x1. Okay?
Yes, I know that this is the definition, but we can't say if it satisfies these conditions, it can be, definitely would have only one minimum or one maximum, because it can go low and low after the
Yes,
x2
but
point.
okay, let me tell you, these methods that we are seeing today, the elimination methods, I am telling you, it's given to you that these elimination methods are used for unimodal functions. So the function that I'll give you will be a unimodal function.
Yeah.
Okay, so this is
Okay,
given
okay.
to you. All right.
So if it's not given, then we
If
can
it's not given,
check it.
if it's not given, this is what you do. You divide it into smaller parts. Okay. So suppose I'll give you some function and I'll ask you to divide it into like, I don't know, 3 parts such that each part would be a unimodal. For example, this is a unimodal, this is a unimodal, and this is a unimodal. If I ask you to find the minimum, right? Every point has a minimum. Each one of these intervals or these smaller parts, they have a minimum point, right? But if you look at it globally together, yes, there are multiple minimum points, right? So I may ask you, okay, I give you a function from, I don't know, 0 to, I don't know, some value x, I don't know, say 100. And I say divide it into 3 smaller parts such that the function, each smaller part is a unimodal function. And then take the first part, okay, and you I don't know, use any of these elimination methods to solve or find the minimum point. Do you understand?
How we can divide if we don't know where are the minimums and maximums?
Well, you can divide by first group, because this is a univariate function. So what you can do is just plot it, just as I did it over here.
But if we plot it, we just can see the minimum and maximum.
You can see the
Then
minimum.
why
Yes,
do we
of
need
course.
this method?
Of course, you can see the minimum, but if I ask you, but you can, I mean, visually you can know where the solution is, but you don't know the exact value, do you? It's not exactly
Okay.
like a 2. You can say, okay, it looks to be somewhere near 2, or it means to be like 2.5, but it's not exact, right?
I see.
Usually you can divide it, right? You can say at 10, I divide it, at 20, I divide it, and I get some function. But if I ask you to find the exact value or approximate value, you need to use these techniques.
Okay.
True?
Okay.
Good. Okay, where were we? Okay, halving method. So everyone, did you understand halving method? It's easy. Any questions? Okay, so interval halving methods. So basically what we do is every time in the first step, we have 3 intervals. So we start with n should be greater than equal to 3. Okay, then after this, it could be any value. So n basically should be greater than equal to 3, and it should be some odd value, because after 3, you choose 2 more, which will be 5. You choose 2 more, which would be 7, and so forth. So n is some odd number greater than or equal to 3. Okay, is that clear? So then this interval, in the end, if I give you some n value, okay, so after, if I say for n is equal to, I don't know, 9, what would be the length of the interval? Using this equation, you can find it. So what you have to do is you have to actually derive and see how I got this equation. Okay, so this is again an exercise. Derive this using this concept that we have seen so far. How do we get this? All right. Okay, so now let's look at our last method for today, Fibonacci method. Do we all know what Fibonacci series is? Guys, Fibonacci. I need you guys to respond. Yes. Hi, Girim. Are you there?
Yes.
Hi, Girim. Gilmanova.
Yes. Yes.
Okay,
yes,
can you tell me what is
I'm
Fibonacci series?
It's like 1 + 1 is 2, 2 + 3, like 5.
So
something like this.
recursively, if you want to write it, can I write it like this?
Yes.
So 1, 1, you add 1, 1, 2, 2 and 1, 3, 3, 2, 5. So every previous two numbers you add becomes your next Fibonacci number. So if this is F0, the first one, this is F1, this is F2, and so forth. So I can say F4, the fourth Fibonacci number is 5, right? Starting with index 0. Okay, so this is basically the recursive equation for finding the Fibonacci series. So is it clear? Anyone doesn't understand or doesn't know Fibonacci? Okay. So now we use Fibonacci method. I, for example, ask you, so in Fibonacci method, basically what I do is I ask you that, okay, you can only do, I don't know, n number of steps. And within n number of steps, I want you to give me what would be the best interval that you can find from, okay? So, so read this and read this. So when it is used. So when you want to use the least number of trials, when you want to have the least number of evaluations, functional evaluations, that's when you use Fibonacci method, okay? So it doesn't have many functional evaluations, and every step it has only, I think, one. So in that way, you use this. So, and also, what is this? Okay, it also works on functions which are not continuous, okay? So because Fibonacci, you can use Fibonacci method to find the interval on functions which are also not continuous. Okay, so let's see how it works. So it is very simple as long as you keep this notation fi and fi minus 1 and fi minus 2 in mind, okay? So again, we are given some interval xs and xf, okay? And we want to find some interval within this, which is a good interval to start off with. And we want, and I'm giving you that you can conduct only n number of experiments, okay? That means you have to find the nth Fibonacci value, okay? So I'm telling you what n is, all right? So what you do is, you know L naught, which is xf minus xs. You calculate x2, okay? And what is x2? x2 is f of n minus 2 divided by f of n times L naught, okay? And given this, so now we know L2 star. So then on a line, on the function, so your first point x1 would be xs, say this is xs, plus L2 star. So this is L2 star, okay? So that means you would get this. Replace, I mean, substitute L2 star here. That would be your new point x1. x2 would be x of f minus this point. So minus L2 star. So this would be x2. Okay? So that means for some Fibonacci value, for some Fibonacci distance from the starting point and from some Fibonacci distance away before the ending point, you actually choose your points x1 and x2. Now, you do the test, unimodality test, okay? So you do the unimodality assumption test and you remove the interval which does not satisfy. So you have x1, x2, do the unimodality test and you remove the interval that is not within the unimodality, which can be eliminated. So what remains would be a smaller area of uncertainty, and that is given by L2. So L2 would be L naught minus L half, okay? So it will be either this part, or it would be this part, okay? This has become very messy. So what you can do is instead of L naught star, you just replace it with L naught, which we have found earlier, factorize it, and this is what you will get eventually. So your new length would be some reduced length of L naught, and that reduced length is actually a ratio. And this ratio is very important because this will later on, we'll see how it is related to the golden ratio that we have seen earlier. Okay, so so for L2, you would have Fn minus 1, Fn L naught, okay? And in this, you would have one experiment. You would either have x1 or x2 within this interval, okay? So basically what you have to do is, again, so, well, we saw this. Okay, so now you find your L2, okay? And now on the other hand, when you have the third experiment in the so now you want to place the third experiment, a new point within the interval L2, okay? And that would be again divided by this, I'm sorry, determined by this function. So now your new point for your new experiment would be L3 star, defined by the ratio of Fn minus 3 divided by Fn, this ratio, times L naught. And again, this ratio can be written in terms of L2, which we have got over here. And this is what so you can write L3 in terms of L2, L2 in terms of L naught, okay? And again, you do the same thing, you find the points where you can actually further reduce it. So if you generalize this for the jth experiment in your Fibonacci method, you would see that L star j would be this, and Lj would be something like this, okay? And if you take the ratio of Lj to L naught for any j value, you would get this ratio. And this ratio is very important because the ratio of Ln to the ratio of L naught is f of 1 to f of n, which is 1 divided by Fn, okay? Now, well, I think, 1 minute, let me, not this guy. This may be a bit, let me copy this. There's this guy, this student, who has explained it well. He has explained this thing with, what to say, with an example. So I would share this link with everyone. Take a look at this guy. It may not be very clear because probably his accent is not very clear, but I definitely recommend you guys to look at his videos. He has prepared good videos on optimization techniques, all the techniques. Okay, so this is the guy. I'll share the link with you over here, and try to follow his video. He explained this. He has put this Fibonacci method in steps, okay, procedural manner, and he has tried to solve it over here. So please look at this video, understand it. If you still have a question in the next session, I will explain or I will cover it, okay? So up till before Fibonacci search, that means not including Fibonacci search, everything else will be included in your final, I'm sorry, in your quiz on Tuesday, okay? So everything except Fibonacci search that we have covered so far, because I feel like you guys need to spend some more time on Fibonacci method. If it's not clear, next class, I will explain it in more details, okay? But for now, first, I want you to listen or look at this guy's video or many other videos. Probably there are, I did not search much, but I saw his video and his video was very simple. So take a look, understand it, and we will again continue on Fibonacci search and golden ratio search in our next session. Any questions so far? Anyone, anything?
No.
Okay, Marat, are you studying?
Good.
I know you're good. I'm sure you're good. Are you studying well?
Yes.
Okay, good. How about Asad? You didn't show us your
Yes,
face
sir.
today, Asad.
I study well, I guess.
You're studying well.
Yes.
Good. I want you guys to study, okay? If something is not clear, just ask me, email me, and I will make sure that at least I prepare something additional to make sure that I cover the topic properly. So Fibonacci search, try to understand it. If not, next class we will study, or we will actually elaborate, and we'll do it in more detail. But it's very simple. Okay, if you just follow that guy's video, I think it's very easy. If not, I will prepare some graphical presentation, and we can again do it on Tuesday. All right. So you have a quiz on Tuesday. So please make sure that you have studied well everything till the beginning of Fibonacci method, search method. Okay.
Okay.
Okay. Take care of yourselves,
Okay.
guys, and thank you very
Thank you.
much.
Thank you.
Bye.
See you later. Thank you.
Bye.
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 Goodbye.